Hello, welcome to Coffees and Conversations. I'm Dr. Alan Wan. I'll be covering the SIMS portions of the slides today, and my partner here, Pat McEwen, will be covering the slides on ToF, XPS, and OJ. We will be talking today about thin film characterization, but we will also give you a brief introduction to urethans for those of you who are not familiar. We will also go through some other details. So, an introduction to our company. EAG has been in service for quite a number of years, 45 years, doing a variety of different materials testing. And we support many clients in all different regions throughout the world. We are secure and also ITAR registered for those doing government contracts and such. We are accredited and certified across multiple industries. And we also have a business continuity plan that includes a global footprint with disaster preparedness and worldwide redundancy, so we can continue servicing you even if one lab has a problem or another. We are owned by the Eurofins Group, and our parent company is quite large, a leader in scientific services with a portfolio of 200,000 validated analytical methods. So basically, we're no stranger to any sort of testings. So to go give you more of an overview, we have a variety of sites throughout the world. Many of them in the US, but also in other places around the world. And in particular, we are starting a battery lab. So we also have the capability to test and also characterize actual batteries and see failures and so on and so forth. We also cover a wide range of industries. We cover semiconductor and as well as semiconductor equipment, but also others, including electronics, aerospace defense, automotive, medical devices, chemicals, telecom, energy, pharma, litigation or patent, as well as raw materials themselves. So we serve the entirety of a life cycle for a product. So not only do we work on things that might be relevant to product information, but we can also do troubleshooting, quality assurance, manufacturing support, failure analysis, regulatory compliance, supply chain quality control, and also patent. So either way, any part of the process of products, we can be called to assist you. A summary of our techniques is listed here on this chart. We call it the SMART chart, which stands for Spectroscopy, Microscopy, Analytical Resolution Tool. Here it is a summary of the analytical spot size, as well as the detection limits for a variety of different techniques. And for those that are only doing imaging, it shows you just the resolution on the bottom. You can also scan the QR code to get a copy of the chart you could download. So each technique has a specific depth of analysis. Again, we will be covering these techniques, so time-flight SIMS, OJ, XPS, as well as dynamic SIMS. The arrows here show that there is a depth profiling option, so we can basically have the sensitivity of the individual technique, but then remove material to gain more access of the underlying layers. So we can use SIMS, for example, all the way from the top surface and all the way down to bulk levels, and similarly for the other techniques that we'll discuss today. So I will talk first about the characterization of ALD thin films by quadrupole SIMS. So the SIMS technique itself has various fundamental components. We have a primary ion source to do the sputtering. We have a mass spectrometer to do the detection, and of course our sample. The primary ion source shoots ions, energetic ions onto the sample, generating a variety of different secondary signals. They can be positive secondary signals, negatively charged secondary signals, or the atoms can leave without a charge, and unfortunately we cannot detect those. So for extraction of these particular type of particle, in this case we'll show the example of a negative ion. We take the electric field to bring it to our mass spectrometer, which could be a variety of different spectrometers. We have 3 different types, either a quadrupole, a time-of-flight, or a magnetic sector. And then we can interpret the data in a variety of ways. So for example, you can scan the M/D ratios to acquire a mass spectra, so give you a general survey of the different elements that are present in the film. We could also do it in imaging mode, so basically by rastering our beam across and collecting data as a function of the raster location, we can acquire an image. But for dynamic SIMS, we typically track the signals from a specific MZ ratio and then acquire them over time. And so as materials are eroded away, we basically come up with a depth profile. And that will be basically the primary purpose of my portion of the slides. So just to go for some of these details, magnetic sector shown on the left, we're using a magnetic field as the analyzer, so basically separating the MZ ratios using a magnet. The quadrupole mass filter instead uses a quadrupole analyzer, basically a high frequency RF field, and that allows us to oscillate specific MZ ratios and then collect those accordingly. So ion yields. So what is happening during the sputtering process? So right there, the cartoon shows that the primary ion implants itself into the surface, ejecting some material from the material, but also leaving behind what you implant. The ionization only happens as a sputter species leaves the surface. So at that point, there's a competition for electrons as the sputter species leave the surface. And then the winner of this competition is determined by the electron affinity of the modified surface. So it's a function of the particle coming out, as well as the work function of the surface itself. We can increase the electron affinity of the surface by implanting oxygen, and this allows us to have a better chance of measuring positive ions, which are typically metals, for example. Similarly, we can decrease the electron affinity of the surface by implanting cesium, and instead we'll have increased our chance of detecting a negative ion. Summary of the all different type of modes we have oxygen bombardment SIMS, cesium SIMS with negative ion detection, as well as MCS+. So the oxygen bombardment SIMS is enhanced ion yields of electropositive species, very useful for doing boron and metal elements. Cesium is similarly particularly useful for the electronegatives, so electronegative dopants such as phosphorus, arsenic, antimony, but also many atmospherics, carbon, oxygen, hydrogen, for example, best detected as negative ions. And then we have the MCS+ mode. That means we are measuring a cluster of the implanted cesium ion with whatever element we choose in a positive ion detection. So this mode allows us to measure some things with less ion yield variation, so a little bit more close to the actual composition of material. And also can be used to analyze elements that don't quite ionize well, as these are positive or negative ions. So some examples of these are like zinc, cadmium, and the noble gases like argon and xenon. So the periodic table is just shown here, and the choice of primary ion, or at least detection mode, is also color-coded. So as expected, many of the metals on the left side are optimally measured as oxygen bombardment as positive ions. And then the non-metals on the right side are conversely detected as negative ions. And then there are a few, as I just mentioned before, some of the metals are best measured as clusters, and all the noble gases are also better detected as cluster ions. So what happens during a depth profile? So during dynamic SIMS, we are removing material, exposing different buried interfaces, and then collecting signals from those interfaces, and then moving on to the next layer, and subsequently collecting these data over time. So, but when we're looking at thin film, it's particularly important to consider the depth resolution of the technique. So with an energetic process, the energy of the primary beam can distort the atoms, basically move them from the original positions, and that's part of the energetic process. If we want to mitigate this, we can use lower primary ion energies. So the diagram on the right actually is a nice example of what happens if we use different primary ion energies on a shallow arsenic implant. At 6 kilovolts, you can see that we can measure the ion uprise. Basically, the front part of the portion seems to be not as quite as distorted, but there's what's called the knock-in effect that basically atoms are further pushed into the sample. So this tail that we have here, this tail is distortion, is all artifact. As we lower the primary ion energy, we can retain more of the original information until finally at the lower primary ion energy at 500 eV, we have much more of the original implant shape of the profile. And then, so there are other types of sputtering considerations, such as the combination of element in the matrix, maybe some sputter-induced roughening effects, as well as crater edge effects that can also compromise depth resolution. But either way, we can tune this and try to get the best type of depth resolution for very thin films. In particular, we can measure thin films down to the angstrom level. So this example shows a thin oxynitride, basically oxide that has some nitridation process. And even between samples that have only a few angstroms difference of actual difference in thickness as well as the nitrogen position, we can resolve those differences. So keep in mind that your thin film can still be quite thin, and we can still get sufficient depth resolution to provide information on your samples. So our general approach for thin films, often these thin films have a request to measure a mix of electropositives, for example, metals, as well. So we will optimize conditions for measuring these in the MCS plus mode. We can then optimize conditions for measuring electronegative species, in particular like atmospherics, again, carbon, hydrogen, nitrogen, well, not nitrogen particularly, but carbon, oxygen, and hydrogen, using cesium negative mode. We can make an overlay profile of these to get an overall picture of all the different elements that are in part of a request. And so then we must line up the profiles to make sure that they display the correct depths, and then we can get full information about our material of interest. This takes significantly more effort than what was considered to be routine SIMS. Routine SIMS usually, like for example, measuring an ion implant in silicon, a single profile with maybe showing one or two elements or a couple of elements at a time. Obviously, when looking at a variety of elements in different modes, this is more costly. So with lower energy sputtering, many of our standards will take a long time to sputter through, so that also is part of the cost. And also, we can take into consideration that many metals may have not very good and negative ion yields, so it becomes harder to actually run the analysis. So for example, we need to rely on signals that might disappear very quickly. So we have to be very skilled at trying to run the negative ion acquisitions, for example, in some of these films, which is part of the cost of doing this. And furthermore, it makes it very difficult to let the machine automate to do the depth profile. So what other considerations we have or other challenges? The films themselves might not be thermodynamically stable. Some metals in particular are very reactive. So for example, copper, moly, titanium will already start oxidizing with exposure to air, and then the additional heat that can even be worse. So sometimes we have to consider whether or not to store the samples in an inert atmosphere or under vacuum or in some other controlled way than just normally in the lab somewhere. Also, on practical considerations include sample charging. So when we have to employ charge compensation, we do that by using an electron beam. But the electron beam itself could also damage some material. So for example, low K films, which are very porous, they tend to collapse under the E-gun. Another thing that can happen is that some atoms may be actually desorbed from the surface by the electrons. This is what's called electron stimulated desorption. This can raise the backgrounds for measuring things such as carbon and hydrogen, for example. Also, as we go through a variety of different materials, very different materials, SIMS is particularly challenging that the secondary electron, not only the secondary ion yield changes, but the secondary electron cross-section can also change. So our charge comp could actually be changing as we go through a complicated stack. So let me just show one particular example. In this case, we are looking at a metal nitride metal stack with a barrier layer being of some sort of titanium silicide nitride, and then some polysilicon with a boron doping. This sample was annealed, and they wanted to look for a cross diffusion of the fluorine that was present in the tungsten silicide, as well as the boron that was present in the polysilicide, whether or not they intermix. So an example of the depth profile is shown here, and this is an overlay of a variety of modes. We can see here in the physical structure shown in this image on the left, TM image of our sample. We can see the fluorine peaks. The fluorine itself seems to have not really penetrated tremendously into the underlying material, and the boron itself certainly has not gone into the top tungsten silicide. So either way, it is important to be able to track where these elements are. So where the fluorine shows up, if it's actually in the silicide nitride layer, and so on and so forth, as well as the boron itself being identified in whichever layer we detected it. So that is the power of using the multiple modes to be able to give us all the signals on one plot. Some additional options and considerations when doing this type of thin film characterization. We could either reduce, lower cost, or expand the scope, higher cost, depending on what you need. So for example, we could simplify the analysis to have only a single mode. However, in that case, we would not be optimized for all the elements. We'd have to have a compromise. One example of being that we would have a poor detection limit for electronegative species if we only use the MCS plus mode. We could use more than just 2 modes. So we could also do positive atomic data using oxygen bombardment, looking for other metal contamination. We could also use a different tool, so a high mass resolution is possible on either a time-of-flight tool or a Kamika tool. This is particularly important if we suspect that some contamination might be a mass interference with something else, and we need to get the true profile. And furthermore, if we need to take a total mass survey without knowing of known elements, we can do that by the ToF tool. We can also remove hydrocarbons in our tool. We basically have an in situ clean in the load lock that allows us to preferentially remove hydrocarbons prior to analysis. Though we have to consider that the sample surface might change a bit due to the in situ plasma being used in this process. And further, if there are very, very fine features, we might want to consider even lower primary ion energies or improved depth of illusion. So keep in mind, this will, of course, increase the sputter time, and so it would increase the cost. But in case you need that much more information, we can also have that conversation. So in summary, the request to characterize thin films often involves measuring a mix of electropositive and electronegative elements, which provides a technical challenge as compared to doing routine SIMS. So we have specialized SIMS protocols to accommodate these requests, which involves taking multiple files and multiple loads, and then producing a single overlay that summarizes all the information requested. This is more time-consuming, higher cost than routine SIMS, and there are a variety of technical challenges involved that make it more difficult than doing, let's say, an ion implant in silicon. But we do have further options to customize the work. We can either increase scope or decrease scope, depending on what you need. And we do highly encourage that you reach out to us. We can have a discussion whenever there's a complicated system so that we can basically sort out the experimental details prior to submission. And so by all means, we encourage you to reach out to us. Okay, with that, I'll pass it over to Pat.
Hi, my name is Pat McEwen. I'll be presenting the second section of thin film characterization. So I've been with the company for about 30 years in various roles and locations. I'm currently here in the Princeton, New Jersey lab, and I take care of all of the Auger requests. So I plan to spend about 5 minutes or so on each of these 3 techniques: Auger electron spectroscopy, X-ray photoelectron spectroscopy, and time-of-flight secondary ion mass spectrometry, and give you some examples of how we use these techniques to characterize thin films. Looking at our depth of analysis chart, you can see ToF-SIMS, Auger, and XPS on the left side of the chart. Analytical chemists love acronyms, so we live in an acronym soup here. And so for AES, XPS, and ToF-SIMS, you can see all of these 3 techniques have sampling depths of under 10 nanometers, so they are optimal for thin film characterization. Alan already talked about sputter depth profiling, and with the 3 arrows you can see on these charts, all 3 of these techniques are also capable of being paired with sputter depth profiling, and we can look at thin films in depth. So if we have structured films, metal layers, adhesion layers, residuals, we can take care of those as well. But with the sampling depth of 1 to 10 nanometers, we can also look at intentional ultra-thin films such as self-assembled monolayers, passivation, plasma-treated surfaces, unintentional thin films, say diffusion to the surface, or other contaminants. On the smart chart, you get a clue as to why we might pick one of these techniques over another based upon the fact that these are occupying different regions of our smart chart. Auger sits in the upper left, so the detection limits for Auger are typically about down to 1.1% atomic percent, but sampling probe size is on the order of about 300 angstroms for the spot size. So for small features, we might select Auger. If we need extremely high or good detection limits, we might go to time of flight SIMS. And for XPS, which gives us slightly better detection limits and a little less spatial resolution, we might choose XPS because it offers some other particular bits of information that I'll get to. I'll start out with Auger, and Auger electron spectroscopy. It's basically the Auger electron was observed back in the 1920s independently by Pierre Auger and Lisa Meitner. So it's called Auger, but we do get requests for Auger and Auger, but it could easily be called Meitner electron spectroscopy as well. And I'm going to just briefly cover what these techniques are without getting into a great deal of detail. But for Auger, we start out with an incident electron beam strikes the surface, and we are going to be collecting the Auger electrons that are emitted from the surface. AES operates similar to an SEM. We can do backscattered secondary electrons. We can also put an EDX detector on there as well. The important thing to note, though, is that for this technique, XPS and ToF-SIMS, only those electrons and the secondaries that escape the solid surface can be detected, and that gives us our thin film sampling depth resolution. Slightly more detail for Auger. It's a complementary technique to EDS. So we have the incident beam removes a core electron. In the EDS, we see the secondary, the photon emission, detect and monitor that. For Auger, it actually involves the emission of a second electron, the Auger electron here. So that core hole is filled, and we have the ejection. So that's a 3-electron process. So the point here is that we cannot detect hydrogen or helium. Same thing applies for a different reason to for XPS. But as I mentioned, the sampling depth in this cross-sectional view shows that only those electrons down to about 50 angstroms can escape the solid surface and get detected. Compare that to the backscattered or the photons, which have a much higher sampling volume. So often, work that comes to Auger started out in the SEM EDS lab, and nothing was seen. Thin film contamination was too thin for EDS. So I'm going to jump right into some examples. This was a Kovar part that came in with a solderability issue. The substrate was not wetting, and in the optical image over here, you can see areas where the surface did not wet, areas where the solder overflowed onto the parts. And sample came in with a variety of possible scenarios as to what the problem was. Went into the SCM lab first, and nothing was really found. We see the Kovar peaks as expected, iron, nickel, a little bit of carbon and nitrogen. In the areas with the solder, we just see the indium and tin, also a little bit of carbon. So the sample came over to Auger, and we looked at the surface here in the SEM image in an area that the wetting was not working out well. And the survey spectrum from this location was dominated by boron, nitrogen, carbon, and oxygen peaks, with some of the Kovar peaks present, but at low levels. Since Auger is a scanning electron probe technique, we can also generate some maps based on, as we see here on the right, and we can see a uniform coverage of the boron, nitrogen, and carbon contaminants, which were not detected at all in the EDS. We also note that the Kovar peaks are present, and since the sampling depth is about 5 nanometers, we know that this is indeed a thin film contamination layer because we can see through it and pick up a little bit of the Kovar peaks. So that didn't really fit into any of the possible scenarios for the client's reasons for the wetting problem that they were experiencing. So we decided to run another secondary technique, XPS, which I'll talk about in a little bit, just to confirm that the presence that there was indeed boron, carbon, nitrogen, and again, because of the similar sampling depths, we see some of the covert peaks present. So once confirmed that this was indeed a boron nitrogen carbon issue, we worked with the client to go through the process and started pulling samples at various points during the process steps to identify the point at which the contaminant was introduced. And then from there, we're able to identify the source. So as Alan already mentioned, a little bit of sputter depth profiling. So we can actually introduce an argon ion beam into the process. So we alternate between etching the surface to remove material and then looking at the composition with the Auger beam. And we did that here, and we can see that as a function of sputter depth, the boron, carbon, nitrogen concentrations drop off quickly within the first 2 to 3 nanometers before hitting the Kovar substrate. A lot of different applications we use Auger for. In this case, just bond pad issues with bonding. In these two examples here, we've got on the left depth profile here, we have a standard typical depth profile for a well-performing bonding sample for an aluminum bond pad. Typically, we find an aluminum oxide layer 4 to 5 nanometers thick with the aluminum oxide present and also some fluoride in there as well. And on the right side, we have a non-bonding problematic bond pad here where the oxide layer is about 1600 nanometers. So there's some corrosion going on here. Looking at the SAM image, you may not notice that. Looking at the surface survey spectra, so at T equals 0, we have very similar concentrations and atoms present. So it's not until we start doing the sputter depth profiling that we reveal the differences between these good and bad bond pads. We do a lot of work on biomaterials, so cleaning passivation processes can be easily monitored. We get nice visuals just like an SEM EDS does, but we also can look at the extent of the cleaning process, any residuals, and the effectiveness of the electropolished surfaces as well, passivation processes. So surface survey spectrum, looking at the outer 5 nanometers, we see very typically carbon, titanium, oxygen, and very little nickel. Reducing the concentration of nickel at the surface is extremely important for a lot of people have, well, some people have nickel sensitivities. And when these things are implanted, it's very critical that surface chemistry is controlled well. Sputter depth profiling, we can actually verify that we have a nice passivation layer here where there's titanium-rich oxide, a little bit of carbon, adventitious carbon probably just from exposure in the ambient lab, and then the nickel-titanium substrate. Very typical sputter depth profile there. XPS, we actually start with an X-ray photoelectron, and we look at the secondary kinetic energies of the photoelectrons escaping the solid. And in this case, we actually have a sampling depth of about 10 nanometers. So similar to Auger, we are looking only at the outer surface. The additional information that we get from XPS over Auger is that we can actually start to see some chemical bonding information, next nearest neighbor chemistry. Auger, pretty much limited to just the elemental composition of the surface. So the example of that is shown here where there's just a thin contamination layer. In our SEM, we have a secondary electron image. We have that in Auger. For XPS, we have a secondary electron image that's generated by the incident X-ray beam. So it's called an SXI. All of those are used to get a visualization of the surface so we can select locations, identify, say, contamination locations on the sample. Survey spectra, so these things can be run just like the Auger point mode, line scan mode, mapping, all of the fun stuff. And we can take survey spectra, the two spectra shown here from the two different regions on and off the contamination. But when we blow up and look at the high resolution, now we can see where the chemistry starts to come in, where we can see the carbon-carbon bonding and carbon-fluorine bonding, start to identify that these are some sort of Teflon fluorocarbon type of contamination on the surface. All of that can be nicely quantified. So we get composition, some bonding information, detection limits down below, at or below 0.1 atomic percent. But we're a little bit limited by the analytical area in XPS. You can focus the X-ray beam down, say, about 30 microns at best. We can couple that with an argon beam, monoatomic ion beams, and these are ideally suited for depth profiling of inorganic materials. And here's an example where we can look at sort of a montage plot of the same sputter depth profile, where you can actually see the chemical state as we go through the profiling through the material. So you can see where we hit the interface between the aluminum oxide, silicon oxide, and the silicon substrate. In all cases, these monatomic ion beams are fairly destructive, so we have a tendency to reduce or destroy the chemistry as we sputter down through it. So we are now working often with gas cluster ion beams. So these GCIBs, which use large clusters of ions to strike the surface and are a lot less destructive and tend to lift off more of the larger chemical species from the sample, leaving less damage on the surface to be tested. So this is just another example where we're actually doing a sputter depth profile of an organic material using XPS and a gas cluster beam. And you can see at various points we can still maintain and have more confidence in the chemistry that we're looking at as a function of sputter depth. The final technique, time-of-flight secondary ion mass spectrometry, can be run in both static and dynamic SIMS modes. As Alan pointed out, he is a dynamic SIMS specialist. But when you take the initial strike of one ion on a surface, that is a static SIMS experiment. We are at a point where we're not actually etching away the surface yet. We're still hitting the outer surface and looking at ideally intact areas. And from that, we have secondary fragments and more molecular ions available. So we keep that dose very low. We can kind of just probe the surface without actually completely consuming and then etching the sample. So that's kind of the realm of when we go from static to dynamic SIMS, is just sort of a somewhat arbitrary value of dose to the sample. Dynamic time-of-flight SIMS operates by, for us, we use a pulsed primary ion source. And as you can see from here, you have the ejection of positive and negative secondary ions. Hopefully we have some intact molecular ions and larger fragments, so we can get the most chemical specificity of these three techniques I'm talking about. Again, Auger, elemental, XPS, we get some chemical bonding, next nearest neighbor information, and with time-of-flight SIMS, hopefully we can get some full organic information about the materials on the surface. Time-of-flight SIMS is the most surface sensitive of the three, with a 1 to 3 nanometer sampling depth. Also provides high mass resolution, so we have some accuracy in identifying the fragments and, again, increasing the molecular specificity. Can be run in depth profile mode, mapping, etc. So that's all pointed out here. The primary beam is rastered around the surface. Like an SEM image or the SXI image, we have a total ion image. So this is just a total secondary ion intensity coming from the surface. From that image, we can then pull spectral data from wherever we want on that sample. Likewise, we have the collective area spectrum over here, the mass spectrum. From that mass spectrum, we can select peaks, groups of peaks, individual peaks, and create maps. So there's a plethora of information within one acquisition in time-of-flight SIMS. Typical example, this again is a thin film contamination on a flat panel display. We have an optical image to the left. Below that is the total ion image. Again, very similar to what we would see in SEM image. Have the mass spectrum over here. And then for people that do time-of-flight SIMS or A lot of types of SIMS, you can become somewhat of a barcode scanner and start to jump out and see peaks at 28, 73, 127, 147 are all peaks associated with silicones, polydimethyl siloxane, PDMS. So you can kind of collect those, map them out, do the same thing for the hydrocarbons. So you can get maps of chemistry on the surface, and then likewise pull the spectral data from each individual area that you'd like. So gas cluster ion beams can also be used in conjunction with time-of-flight SIMS to do sputter depth profiling. And this is kind of a little bit of a goal for many years, because the interest is to look at organic layers, might be drug-eluting stents or paint systems on for cars or whatnot, looking at distribution of molecular organic species within organic coatings is really of great interest. And this is an example using a GCIB to sputter depth profile through a stack of organic, thin organic components. Different Ergonox materials, Ergonox 1010, Ergonox 3114. These are all additives typically used in plastics. So we can see that here. So these 50 nanometer films doing a sputter depth profile and maintaining the organic information as a function of depth. So in summary, I hope I've kind of shown through these examples that all of these techniques are ideally suited for thin film characterization because of their surface sensitivity, and from 0 to 10 nanometers for sampling depth. They all have good sampling depth resolution. They all can be run in a depth profiling mode. XPS gives us good quantification. We get very little quantification from ToF-SIMS unless we have standards. Auger can be quantified, but best again with standards. All of these can be run in line scan, point scan, mapping, and sputter depth profiling modes. Auger gives us the best analytical area of about 30 nanometers. ToF-SIMS gives us the best sensitivity for parts per million, parts per billion detection limits. XPS gives us the most chemical, chemical bonding information. ToF-SIMS the most chemical specificity. Limitations are all similar for the techniques. They're all require that samples be UHV compatible, although we do have cold stage options. So if we're looking at something, say like an intraocular lens that is wetted surface, we can freeze these, maintain the surface chemistry in vacuum conditions in the frozen state. Limitations also, hydrogen and helium are not detected, as I mentioned, Auger and XPS. And then for time-of-flight SIMS, the limitation is that the quantification is limited. Sometimes it's too surface sensitive. A tiny bit of contamination created during sample prep or packaging can cover everything that we're actually looking to see. And sometimes the organic information can be limited. Samples that have been through a heating process or something where the organic information is now lost because of a heating process or something of that sort. So with that, I'm going to wrap it up. Why people choose EAG? Client confidentiality is a very important core component to our business. We have just NDAs with most of our clients, but it is always assumed that the information is confidential. We have analysts that are considered leaders in investigative science in many fields. We have hundreds of years of experience throughout each of these techniques throughout the labs. A lot of people in the company have origins in different areas. Some people come from biology, some people from geology, material science, physics, chemists. So there's always somebody that we can rely on if we need additional support to understand the problems that are coming in. We have a full array, as Alan pointed out, of techniques available. So we have a very much a multidisciplinary approach to helping solve problems. We can often scale to the demands to meet time constraints. A lot of options for quick turnaround. We have over 2,500 instruments worldwide, duplicity in various sites. And we are considered the global leaders for materials and testing services. So with that, I'd like to wrap it up. We're going to open up the floor for questions, and thank you for your time.